All right, so if you notice, the parts A and D are the same for every single one that we did. Basically what it means is if I have some function, we'll call it f prime. If I have some function f prime, and I want to find the area under that curve, then I can find the antiderivative, which would be f, right? We're just going one step up in the totem pole. So if I have f prime, and I want to find the area under the curve of f prime, I go one step up and I find f, and then I evaluate f at the endpoints that I want to find the area under, so like from 1 to 4. And I would start with the final endpoint, 4, and I would subtract the initial endpoint. So basically that's what the fundamental theorem of calculus says. So it sounds really big and scary, but really all it means is that if I have this function, f prime, and I want to find the area under the curve, I find the antiderivative, so I go up one step, and then I evaluate that antiderivative from the final point, and subtract the initial point from it, and that gives me the area under the curve, which is actually really cool. So let's see how that actually works. I want to find the area under the curve of this. Well, we already know how to integrate this, this function, so let's just go ahead and integrate it. So we've got the integral from 0 to 4. Now you don't want to forget to put your limits on there, because this is a definite integral, not an indefinite integral. So you're always going to keep your limits of integration on the function. So this is 2y to the 1/2 plus 1 dy. And so that would be, the actual integral is 2y to the 3/2 over 3/2 plus y. And guess what? Right now we don't actually have to put plus c, because we're going to actually evaluate it at this point. And so all we do is we write this little bar here, and we say we're going to evaluate from 0 to 4. That's really important notation for you to recognize. So this means I'm evaluating from 0 to 4. Okay, so when you do a definite integral, you add that onto the end so that you can see that I still need to evaluate it. So let's clean this up a little bit. That's 4/3 y to the 3/2 plus y evaluated from 0 to 4. And the way we evaluate this from 0 to 4 is we take the final value, 4, and we subtract the initial value, 0. Okay, so the final value would be this function at 4. So that would be 8 times 4/3, which is 32/3, plus 4, which gives us 44/3. And then what's the value at 0? Well, it's 0. So I do f of 4 minus f of 0, which is 44/3, minus 0, which is 44/3. So the area under the curve of this function is 44/3. Let's take a look at this one. Now this one's going to take a USubstitution. It's going to be just a little bit different. But let's go ahead and integrate it. Well, so I'm going to say u equals 4t plus 1. So du, if I differentiate both sides, I get 4 dt, right, because I differentiated with respect to t. And so I'm going to get dt by itself, so du over 4 equals dt. So now I'm going to rewrite the integral in terms of u. Now here's the problem though. My limits of integration are in terms of t. My limits of integration are in terms of t, not in terms of u. So I can't legally put those limits of integration on there, because that's not right. I'm not integrating with respect, or from 0 to 1 anymore, right? Because u does not equal t. What does u equal? Well, u equals 4t plus 1. So when t equals 1, could I find out what u equals? Absolutely. So when t equals 1, or 0, let's start with that. When t equals 0, u equals 1. So instead of a lower limit of 0, we now have a lower limit of 1. When t equals 1, u equals 5. So I now have an upper limit of 5. So super, super important anytime you do a u-sub, you need to change your limits of integration to be u values, not t values, because once I integrate this function, it's going to be in terms of u, and then if I didn't change my limits of integration, I'd have to go back in terms of t. But the cool thing about this is I don't have to go back in terms of t now, right? I just told you what u equals, so now I can just integrate it. I don't ever even have to change it back into t again. So let's go ahead and integrate this. So the integral of that, let's clean it up a little bit. We've got 1/4 times u to the 5th du from 1 to 5. So we're going to integrate that, and it's going to be 1/4 u to the 6th over 6. Again, not plus c, it's evaluated from 1 to 5. So that equals 1/24 u to the 6th, evaluated from 1 to 5. And then I'm just going to evaluate it, right? So, good on you if you know what 5 to the 6th is in your head. I don't. Okay, so we're going to go ahead, and 5 to the 6th is 15,625 over 24. So that is f of 5 minus f of 1, which is 1/24. So that's 15,624 over 24, and I have a feeling that simplifies. Should we simplify it? I'm not sure that it matters. Minus 1 divided by 24. Oh, it actually simplifies really nicely. So that is 651. If it didn't simplify, you could have left it just like that. You wouldn't have to keep simplifying it over and over. But that's the value under the curve of that. Isn't that cool that you don't even have to put the t back in? You can just, if you change those limits of integration to match your u, then your u sub is just valid and you just leave it. So here's another u sub. So we've got, let's see, let's call u is going to be 2x minus 1. So du is going to be 2 dx. And our problem is that, let's sub this in first, and then I think the problem will become more apparent. So we divide both sides by 2, and our dx equals du over 2. So we have our integration, and we'll change our limits here in a second. Square root of u du over 2. And do you see our problem? We still have an x. That pesky little x is still there. So we need that x in terms of u. And this one's just a little tricky to remember to do this, but we can go ahead and manipulate our substitution up here, that we have up here. We can manipulate that to give us what just x equals, right? So we're going to add 1 to both sides, divide by 2. So x equals u plus 1 over 2. So anywhere I see an x, I can put in u plus 1 over 2. Let's go ahead and do that. So this is the integral of u plus 1 over 2. We're just going to go ahead and split this out so that it's just a little bit easier to see. So then we have some constants here we can go ahead and get rid of. You know what, before we do that, let's go ahead and change our limits of integration, because it's really bad that we have this like blank integral right here if we have a definite integral. So when x equals 1, what does y equal? Well, 2 times 1 is 2 minus 1 is 1. So the new limit is also 1. And then when x equals 5, we've got 10 minus 1, which is 9. So we're going to evaluate this from 1 to 9, which again makes it just so nice. Okay, So we're going to just go ahead and take out some of these constants. See, I have a 1/2 times a 1/2, so that's going to come out as a 1/4. And then I have u plus 1 times du on top, and put u on the bottom. So then we can simplify this some more. We can write it as 1/4 times the integral 1 to 9 of u plus 1 times u to the negative 1/2 du. And then we can do some algebra, which gives us u to the 1/2 plus u to the negative 1/2 du. And then, do you see how this is going to be like so much easier to not have to sub in, back in all of that stuff? And when we do more complicated u subs, it's so great. So, then we just need to integrate it. So we have 1/4 u to the 3/2, okay, 1/4 is times everything, over 3/2, plus u to the 1/2 over 1/2, evaluated from 1 to 9. So you're either writing a plus c or you're writing that bar. Those are your only two options when you integrate. You need to write something at the end. So like if you're getting to the end and you're like, la-di-da, done. No, you're not. Sure not done. Okay, so let's simplify this some more. We've got 1/4 times the whole thing, and that's going to be 2/3 u to the 3/2 plus 2 u to the 1/2, evaluated from 1 to 9. So then we could even multiply those in, and we get 1/6 u to the 3/2 plus 1/2 u to the 1/2, evaluated from 1 to 9. So this is where you guys are going to get tripped up, is in the algebra. Okay, so we've got there, and now I think we can finally evaluate. We can just go ahead and start evaluating. So 9 to the 3/2 is 27, divided by 6. 6 is 9/2, and then 9 to the 1/2. 9 to the 1/2. I almost typed that into my calculator. That's 3 times 1/2 is 3/2. Okay, so this right here is just f of 9, right? So I evaluated f of 9. Now I need to subtract f of 1. Super important that we keep track of all of this. Okay, so then I need to subtract f of 1, which is 1/6 plus 1/2. So then I can just start doing some more algebra. That's 12/2, which is 6, minus, let's see, 1/2 is 3/6, so 4/6, which is 2/3. And yeah, yep, I'm still on the right path. Whew. All this algebra, like I had to write it down first to make sure that I like did it right in the moment. So then we've got that's 6. 6 minus 2/3. 6 is 18/3 minus 2/3 gives us 16/3. Whoo, that's satisfying. Let's look at that problem. Look at this problem. Wow. Okay, we did it. There you go. So, again, what we did is we did a USubstitution. We did a USubstitution. We changed our limits of integration. Then we simplified, did some algebra, did some more algebra, did some more algebra. Then we took the integral. Then we simplified. Then we evaluated, we simplified one more time. Then we evaluated f of 9 minus f of 1 using the fundamental theorem of calculus. Sorry, not fundamental theorem of algebra. That's a totally different fundamental theorem. And then we did the algebra to find that. So the area under the curve of this graph from 1 to 5 is 16/3.